Hello, my name is Joe Vasta, and we're going to talk about integration by parts. We have this formula that says integral u dv equals uv minus integral v du. And what we're going to do is we're going to take a look at how to do this using a table. So first of all, we make this little staircase here. Well, just one step, and you put the derivative, d for derivative, I for the integral. Then what we're going to do is we're going to put u under the derivative column and dv under the integral or the antiderivative column. And then we'll take the derivative of u, which is du, we put it underneath that, and take the antiderivative of dv, which is just v. We're going to go ahead and we're going to do something. We're going to put a plus there and a minus there. We're going to go back to this formula here and take a look at it as we look at this little table here. So integral u dv, so whenever there's an integral, we have sort of a diagonal here. Well, what this is going to equal is uv, so whenever it's along a row, we multiply, and then minus, so now here's a diagonal again, and we're taking the integral. So what I want to do is put a little analogy in your head. When you do integration by parts and you use this little table method, it's like you have to turn on the machine. So, like it's some sort of lawnmower or whatever, and it gets going, and then you're cranking away, and you can turn the machine off right here, and it shuts the machine right off. And that's basically how you do integration by parts using a table. And I know you have to see some examples because this is very general. Before we move on to our first example, let's show you the Lyautey. Lyautey is the order in which you put these functions here. The first function, the u and the dv, that's what we'll use to pick the u and the dv, where L stands for logarithmic, I for inverse trigonometric, A for algebraic, T for trigonometric, and E for exponential. And so we'll get into that as we do some examples. So now we're ready for our first example with integration by parts, and we're going to kind of do it in this template here. The integral of 3x times e raised to the x over 2 power. So that's what we're doing. We put our Lyautey there, and this 3x is algebraic, and this e raised to the x over 2, that's exponential. So algebraic covers all the polynomials and things like that. So let's go ahead and color code those. And because the yellow one, the algebraic, is to the left of the exponential, we are going to choose this one right here to be the algebraic one. So 3x is going to go right there. And the other part, the exponential part, is going to go right there under the integral. So what am I going to do with this 3x? I'm going to go ahead and take the derivative, put it right below, which is 3. And then I'm going to go ahead and take the antiderivative of e to the raised to the power x over 2. You've got to do some u substitution, and you're going to get 2e raised to the x over 2 power. Let's go ahead and adjust our plus minuses. Always starts with a plus and a minus, and we're ready to start the machine. So when we start the machine, here it goes. There's the green part right there. So the machine has just been started, and we're going to say this equals when we multiply those two functions together, so 2 times 3, that's where we're getting the 6, and then we have an x and e raised to the x over 2 power. And then we're going to shut off the machine by doing that, multiplying those together, and notice there's the minus sign, which is right there, and that's incorporated in the integration by parts formula. Okay, so let's go ahead and integrate this thing, 6e raised to the x over 2 power. You'll do a little u substitution, and you'll get minus 12e raised to the x over 2 power. So what I'm going to ask you to do is come back over here to this table and take the integral of this 2e raised to the x over 2 power, and we end up getting 4 times that. Well, notice something, that if you multiply those guys together, you get negative 12e raised to the x over 2 power, which is right there. So what we could do is we could take away this little rectangle, those two rectangles, and we can do our integration by parts like this, where we say the integral of that green thing is, then we have the blue circle and the purple circle. Now, we could have kept taking derivatives in this derivative column and integrating in the integral column, and then we go ahead and put the plus there, and that product is just going to be 0 times something, which is 0. Now, if we kept the machine running, we'd have another 0 here where my pointer is, and another 0 down here, and another 0 down here, so you would just have zeros down the rest of the way if you kept filling out this table. So we don't need to do that anymore, and we have our final answer. Now, lots of times you'll go, oh, well, Joe, you forgot to put the plus C. I'm going to save that until the very end because I want to concentrate on this method. So here is our answer. We have the integration by parts. So for the next one, I'm going to turn the machine on, and I'm just going to leave it running until I get a 0 there. And then I don't have to do this part right here. I'll just go ahead and read off what's on the table. So let's go ahead, take a look at our next example. Here it is, the integral of x cubed sine x dx. We put our Liotte there. We see that the x cubed is algebraic and the sine x is trigonometric. So I'm going to put the x cubed right there, and the sine x I'm going to put right for the integral column. So we put them in the same order of which we see the Liotte here. So this algebraic is on the left, this trigonometric is on the right, and that's how we do it. So now what I'm going to do is I'm going to go ahead and take the derivative of this thing. So I get 3x squared, 6x, 6, 0. Now, if I keep going, I'm just going to get 0, 0, 0. So I'm going to stop right there at that first 0. And now I'm going to go ahead and take the integral of sine x. That's going to be negative cosine. Integral of negative cosine is negative sine. And then keep integrating. So we have the cosine, the sine, and negative cosine. Let's not forget our pluses and minuses. So plus, minus, etc. So those alternate. And the reason we put those is because our integration by parts formula, the original one we were working with, it said uv minus integral v du. Well, that's where this minus is coming from. So this is one of the integration by parts problems. If you weren't using the table, you'd have to apply integration by parts more than one time. So I think it's time to start the machine. And there it is. So now the machine is running. So it's like going, you know, it's just, I mean, it's gas powered or whatever you want it. And it's like, and it's running. And so here it goes. This is what the machine kicks out. Negative x cubed cosine x. Okay, so then we come down here and we multiply those together. So that's a negative times a negative. We have 3x squared sine x. Now, here's the deal. At any time like right now we're on this one, at any time we can turn the machine off, provided that when we multiply those together, we put the integral sign. Now that would be kind of silly to turn the machine off at this point, because we could just keep the machine running until it gets down to 0 and not have to do any integration here. So I'm going to actually undo that move. So what we're going to do is we're going to keep it running by multiplying. So there's that one there, 6x cosine x, and then we have a minus 6 sine x. And then down here, well, we really don't have to write this, but you have a 0. So our final answer on this is that right there. We put our plus c there. Let's go to the next problem. Oh, here's the one where people don't like. It has an LX in there, so we go ahead and we do our Lyautey. We have a logarithmic and an algebraic. And notice the logarithmic, that's the one that's going to go on the left. Okay, so we have the log, natural log of x, and x. Now, some people would say, well, put x here and the ln x here, and then zero out the derivatives eventually. Well, then the problem is you have to take the integral of ln x, which would then require an integration by parts. And so would this part here. So that's why we have this Lyautey thing. Okay, so what we're going to do is we're going to take some derivatives of ln x. Now, if you remember the derivative of ln x, it's 1 over x. And the derivative of 1 over x, I'm not going to go through it here in this video, but it's 1 over x is x to the negative 1. So you go ahead and do the power rule and you clean up the algebra, make your exponents positive, and you end up getting negative 1 over x squared. The next one is 2 over x cubed, negative 6 over x to the 4th. And this appears like it's never going to zero out, so that's concerning. But we'll just keep going with this. Now we're going to go ahead and take the antiderivative of x. That's x squared over 2. Take another antiderivative. X cubed over 6. X to the 4th over 24. X to the 5th over 120. X to the 6th over 720. Notice the denominators are factorials. If you're like, what is that? It's not that important. I guess it kind of is. Like 4 factorial is this. 4 times 3 times 2 times 1. Okay. Let's put our plus and minus. We alternate those signs. And start the machine. So we start this machine. And our first term is going to be x squared ln x over 2. You just multiply those. Well, we keep this machine running. And it just keeps running. And this is going to keep running forever. So this is actually kind of scary. I'm going to take all the terms except the first term, and I'm going to factor an x squared out of those. I could use the first term, but I just want to focus on those other terms. I'll factor out a negative x squared, and I have a 1/6 plus 1 over 24 plus 1 over 60 plus 1 over 120 plus yada, yada, yada. Now, this is actually kind of sad because it's an infinite series. So on the very last slide of this PowerPoint, I'm going to go over how you compute that. But if you were able to compute that infinite series, you would end up getting inside those parentheses 1/4. So on the very last slide, I'll go ahead and show you how I got that. And so this gives us the answer. Now, we definitely don't want to do our integration by parts using infinite series when there is an easier way of getting this problem done. So let's go ahead and do problem number 3 again. So here it is. So we go over the Lyautey. We've done this before. ln goes on the derivative, x goes there. I'll take a derivative, I'll take 2 integrals, I'll put my pluses and minuses. So how would we do this problem again? I would start the machine, let it run one time, And then when I get down here, I'm going to stop the machine. And when I stop the machine, I have to put an integral sign. So now all I have to do is take the integral of 1/2 x, and there's a negative in front, so this is negative x squared over 4, which is exactly what we got on the last page, but we did not have to evaluate an infinite series. Let's go ahead and do the next problem. So look at this. It says integral e to the x sine x. These are these weird problems where I guess you have to do something called the round robin, and it's kind of a weird problem the first time I saw it. It also inspired the song. Well, it's really Piano Man, but there's a guy named Hilbert Geezer who sings a song about this. Well, part of the song is about this. There he is, 10 o'clock on a Friday morn. You can read it. You could probably go on YouTube and find Hilbert Geezer singing this. But note the last line. I mean, there's a student who can't do an integral. There's trig and there's e, and I just couldn't see how to do integration by parts. And so that's what we're going to tackle in example number 4. So let's get back to it. So there it is. I'm going to do a Lyautey. I have exponential, that's e to the x, and trigonometric, which is sine x. So I'm going to go ahead and put the e to the x. Oh, that's not the e to the x. I'm going to put the sine x. Okay, so I wasn't thinking. I'm going to put the sine x there because trig is on the left side and exponential is on the right side. So we'll go ahead and take some derivatives of the sine. Derivative of sine is cosine. Derivative of cosine is negative sine. We can keep going. This one's not going to die out to 0, but I'm going to stop right there. Now I'm going to do the antiderivative of e to the x, which is e to the x, and then e to the x, and then e to the x. We'll put the plus and minuses down. Now, with this integral, I'm going to set it equal to I, and I could have done this on the other examples, and we're going to start the machine. So the machine has started. I put the I equals right there, and let's write out the first term. E to the x sine x, and then we keep the machine going, minus e to the x cosine x. Okay, so now we're down here. We're going to stop the machine. So watch what happens when I stop it. I get minus integral e to the x sine x dx. Well, doesn't that look familiar? Integral e to the x sine x dx, that's our original problem. That is what I equals. So let's replace that with an I. So now I have this equation, and I'm trying to solve for I, which is the integral. The original integral, I'm going to add I to both sides. I'm going to divide by 2, and that's my answer. So we put the plus c there. That's how you do integration by parts using the table. So I think I owe you one last explanation of that infinite series if you're interested. If you're not, this is a very good time to stop the video. Okay, so we have 1/6 plus 1 over 24 plus 1 over 60 plus 1 over 120. I'm going to kind of do a sloppy job on this. We could be more precise, but I just want to show you that this thing's going to add up to 1/4. So first of all, I make the realization that 6 is 1 times 2 times 3, and 24 is 2 times 3 times 4, and 60 is 3 times 4 times 5, and then etc. Now, if you actually wrote out where we were getting this from and we were multiplying to get those numbers, we had some factorials, but they weren't completely going to be full when you divide by the top. So go back and look at the other one if you're wondering kind of like where is this coming from. But I wrote it all out. And now I'm going to use the summation notation for this infinite series. And so there's summation notation. And you can put n equals 1 in there, and you'll see that you get this first term. Now I'm going to do something where I'm not going to write out all the work here, but it's a partial fraction decomposition of that fraction. And I end up getting 1/2 over n minus 1 over n plus 1 plus 1/2 over n plus 2. I'm going to factor a 1/2 out in front of the summation sign. And some of the stuff turned blue because I'm going to focus on that now. I just did that because I didn't want fractions in here. I mean, fractions within the numerators. So now that looks a little prettier. And I'm going to put n equals 1 in there, and n equals 2, and n equals 3. I'm going to write out all the terms over here. So let's go ahead and do that. And as you can see, so I wrote up all the terms. Now notice the first two columns add up to 1/2. This is called a telescoping series. And if you had calculus 2, you might have seen this. Look at the next column. We have a 1/3, a 1/3, and a 2/3. That adds up to 0. And the next column adds up to 0, adds up to 0, adds up to 0, adds up to 0. So this infinite series, the whole thing adds up to 1/2. So I have 1/2 times 1/2, which gives me 1/4. So this concludes the video. I hope you enjoyed it. Have a good day.